Welcome back. And the topic today is just a continuation of this full configuration interaction theory. We're going to look at the diagrammatic representation as well, because that's something which is widely used in many body physics. One of the things which I want to do was actually to give you a quick repeat of what we went through. So if you look at the weekly material which we have, you will find a rough repetition of and setup of the equations which we went through. So I'm just going to skip some of these first equations, first slides here, and then just move over to the material which we covered yesterday. So let me just get quickly to the formalism which we worked on, and which is going to keep us, how to say, busy with the rest of the semester. This kind of formalism which we introduced, where we have a general ground state which is now defined in terms of these creation operators, and then we have a one particle one hole state, a two particle two hole state, and then we have an n particle n hole states, and these are all represented by these types of creation and annihilation operators. And then what we did was to expand the ground state wave function, the exact one. So we assume this is the solution to the many-body problem. And then we expanded this in a basis of Slater determinants, where we assume that this basis is an eigenbasis of the non-interacting part of the Hamiltonian. So this is a pretty common choice in many-body physics. And then we could rewrite everything in terms of this so-called correlation operator, which then contains all these creation and annihilation operators representing one particle, one hole, two particle, two hole, etc. excitations. And it's pretty common to set this constant C 0 to 1, and it's normally called intermediate normalization. And then we could rewrite the wave function for the ground state in terms of 1 plus this correlation operator. And when we diagonalize, we get these coefficients as the different elements of an eigenvector. And then with these coefficients, we can calculate the exact energy. Normally, we get the energy when we diagonalize, but you can also take these coefficients and see if you get the same energy as you get when you diagonalize. The equation which you have here is something which you can easily extend to any other state, because you have an orthogonal basis, and then you can expand any state in that basis. And that's a basic assumption which we are going to keep with us for the rest of the semester. And then we rewrote this one in a more compact way, where we have this coefficients which we get from the diagonalization, and we define this A of HP as the chain of creation and annihilation operators. And if we move on a little bit, so I'm not going to repeat everything. This is just the diagonalization problem which we end up with. But the thing I wanted to say a little bit about is actually this type of inefficient way of solving the eigenvalue problem which we began with yesterday. And I wanted to repeat a little bit some of these basic elements. So one of the things we did then was to calculate the first row in this Hamiltonian matrix and multiply that one with the eigenvectors which we have in terms of the coefficients. And when we did that, what we did was simply to multiply with phi 0, which is the first row, and then we multiply with this Schrödinger equation which we have here, E minus E, and then we got an equation where this H which we have here defines the so-called reference energy, and this E0 or E here is actually the exact energy, and all the other terms actually don't contain E because these are orthogonal states to phi 0. So this ends up being H here, and then we have only H here, so we're calculating this transition matrix element. And then we have the so-called reference energy, which here is labeled as E0, and the exact one is E. And this defines the so-called correlation energy. And if we stay with a two-body interaction only, this is the only two terms which survive. Now, this is a compact way of setting up the correlation energy. And if we have these coefficients, we obviously have the exact correlation energy. But in general, we are going to look at approximations to these coefficients. And so you can actually view many of the other many-body methods in terms of ways to find new expressions for these coefficients which you see here. So that's a kind of overarching message. And when we come to Hartree-Fock theory, we are going to find an equation for this one. When we go to many-body perturbation theory, we will have an expression for this and also for these coefficients, etc., etc. So just keep this in mind for later. And then what we did was to just rewrite these equations in terms of the matrix elements which we have found. So I think I went one slide back actually. Yeah, that defines the correlation energy. And when we then plugged in the matrix elements, which we calculated earlier, we could rewrite it in terms of this one body matrix element where we have this operator F, which then contains a medium correction to the motion of a particle. And then we have the one body part, which comes from the kinetic energy and an eventual external potential. And then we have the two-body term here, where we can plug in the explicit matrix elements, or integrals, which is a more correct way of saying it. But we sloppily are going to call this for just matrix elements. And then we could repeat that exercise, and we have the second row in the Hamiltonian matrix where we multiply with a one particle, one whole state, just one of them. And when we reorganize everything, we end up with this one body piece, which we have here, which we have already calculated. And in case this F has these states as eigenstates, this is going to be 0. But normally we can assume that it's non-zero. And then we have this term here, which multiplies with the unknown coefficients. So these are unknown coefficients. And then we have the higher order terms, and then we have the coefficient again multiplied with the energy. Now, since this energy depends on the coefficients as well, this becomes a non-linear equation in the unknown coefficients. When you diagonalize, you get them, obviously. But in general, this is just a way of rewriting the same equations which you would diagonalize, but setting it up as a set of coupled non-linear equations. So this is your second row. If you go back and look at the first row, if you add the energy, gives you actually this term here. And so these are coupled equations because the unknown quantities appear in all the equations which we have, or in almost all the equations, because when I multiply here, I get terms with the free particle, free hole excitations, two particle, two hole, and one particle, one hole. When I go to the third row, where I multiply with a two particle, two hole state from the left, then I will get the coefficients CIA, one particle, one hole mixing, two particle, two hole mixing, three particle, three hole, and four particle, four hole mixing. So gradually then I will bring in more and more coefficients row by row. And that will set up a set of equations which are coupled and are non-linear in the unknown coefficients. Now, what is pretty common to do then is actually to use an approximation here. And we are coming back to this when we are going to discuss many-body perturbation theory. So many-body perturbation theory gives an explicit expression for this coefficient. And this is something we come back to. And then you can actually make an ansatz for the coefficients and you can start iterating. The reason why I bring this up is that we will also discuss another many-body method, which is called coupled cluster theory. And in coupled cluster theory, one of the things we will be doing, for instance, for this equation here, is that we will keep the equation for one particle, one hole excitations and two particle, two hole excitations, and we will zero out all the other ones. So we will mainly be interested in a set of particle hole excitations. So that means that we will get expressions for the coefficients for the one particle, one hole piece and two particle, two hole piece. So you will probably not see the full reach of this before we come to many-body perturbation theory and coupled cluster theory and other many-body methods. But I'm just mentioning it now because these are common approximations for the first iteration here. So if you go back to this equation you had, you would then zero out these terms with a 2-particle 2-hole and 3-particle 3-hole, and you would simply plug in that coefficient here and here. And then you would then solve this equation, because then you have an ansatz for it. And then you would start iterating, because then you have an approximation. You get a result for the energy. So you get this delta E because you have an ansatz here. And then you can use that delta E in the equations here. And then you start iterating. Then in the next iterations, you will also find the results for the 2-particle 2-hole piece. So if I do the same exercise, and we didn't do that in the on the whiteboard yesterday, because this gets very meticulous. So I just put up the expressions here. So you would do the same thing here, and you multiply from, this is the 3rd row in the Hamiltonian matrix. You multiply with this guy here. You get the 1-particle 1-hole linked with a 2-particle 2-hole. The term E will disappear because these states are orthogonal, but there will be a term E which comes from this term, because here you can have an overlap between these states, which can be equal to 1. And then you have 2-particle 2-hole and 4-particle 4-hole. And this continues. So as I said, it's a highly inefficient way to solve the diagonalization problem. And the number of floating point operations is normally much larger than using a diagonalization algorithm, which typically goes like 4 divided by 3 times n cubed, where n is the dimensionality of the matrix. That's the number of floating point operations you typically end up with. But here again, you can put all these terms here, 3-particle 3-hole and 4-particle 4-hole to 0. And you can use many-body perturbation theory. And there as well, you would have a simple ansatz in the first iteration for that. So many-body perturbation theory is actually going to give us this expression here. And this is something we will derive explicitly a little bit later. So if we now want to summarize many or full configuration interaction theory, if you can diagonalize the large matrices, this is the method of choice. It gives all eigenvalues, ground state and excited states. The eigenvectors are simply obtained directly from the coefficients. And you can compute easily expectation values of other operators because you have the wave function. So if you're looking at some transition probabilities with a specific operator, you have immediately the wave function from the diagonalization. Or rather, it's better to call it the eigenvectors. So wave function is something which I try to keep to a solution which is time dependent. So I normally call this state functions or just eigenfunction. Correlations can easily be understood in terms of contributions to a given operator beyond what we will call the Hartree-Fock contribution. And I'm going to discuss this. We're going to start to scratch the surface of Hartree-Fock theory in the end of the lecture today. And this is something which we will start with next week. The thing which I just wanted to remind you of is that we can define now the correlation energy in terms of the expressions which you see here. So the thing which, when we now move into Hartree-Fock calculations, is that then we can actually define a new vacuum result, which hopefully is better than the one we started with. And then that means that we are going to find single particle states here, which will end up being eigensolutions of this operator F. If then the single particle bases A and I are eigen states of this F, this means that this term here is 0. And then the only term which survives is this one. So there will be terms then which get so-called renormalized, in the sense that when we perform a new basic calculation with a new basis, these elements here, these integrals will change because this single particle wave function will change. And what happens then is that we get a result which hopefully is get closer to the optimal eigenvalue using the variational principle. So everything we have done now with full configuration interaction theory when you don't make any truncations, and the theory to come, Hartree-Fock theory, they are going to be explicitly variational theories if you don't make any truncations. When we come to many-body perturbation theory, that is going to break the variational principle, which means also that the theory is not going to be, the Hamiltonian you get may not be Hermitian. And that can lead to problems. Okay, so I also wanted to, in connection with the exercises today, I wanted also to point back to some formalities which we had in the very beginning of the semester. So let me go back to the very beginning and remind you of some of the things before we begin with so let me just bring up a new slide here. There are some technicalities which I actually wanted to bring up. And if we go back to the very beginning of the semester, there are some technicalities about orthogonal basis and single particle basis and many-body basis. And this is something which is also relevant for the exercises this week. So let me just scroll down a little bit, because there's something which we didn't discuss in much detail in the very beginning, but this is related both to what is going to come now with Hartree-Fock theory, but it's also relevant for the exercises this week. So one of the things which we have done is to simply define a new basis in terms of a previous basis. This is a pretty common technique, and where we assume that this basis is orthogonal, and these coefficients which you have here, they belong to a unitary transformation. So I'm going to repeat a little bit about unitary transformations later, but that means that the transpose of the matrix is equal to the inverse of the matrix. It means also when I take the transpose times the matrix, the original matrix, I get the identity matrix. And this basis sets are assumed to be the eigenbasis of this part of the Hamiltonian. So this is a single particle basis. And you can easily show that if you have an orthogonal basis, like a vector here, and then you calculate the inner product, and you apply an orthogonal or unitary transformation. So in quantum mechanics, we are interested in unitary transformations because the wave functions are complex. But in case all the coefficients are real, you can just stay with an orthogonal transformation. But what we have then, when we have a typical transformation of the basis, we know that orthogonality is preserved. So this is one of the things you would need in the exercise this week. So just take a look back at the very beginning of the semester. There are some kind of technicalities which we didn't discuss in detail. Now, you can then easily show that if the basis is orthogonal and normalized, as we have here, it doesn't need to be normalized, but a unitary transformation preserves orthogonality. So you will see that quickly, because when you then set up the new basis, which is given by this one, you can easily show that this preserves orthogonality and normalization. I will, as we said in the beginning, I will just call this basis for orthonormal. That's a pretty common shorthand. Now, one thing which is interesting for us is the many-body basis, and this is related more to the exercises. So if we just write it like this, if you think of a determinant, the thing which is important is if we now have a linear combination here between coefficients of a determinant, you can actually show that this relation here applies. So if you look at the expression which you have here, you could now think that you have an original Slater determinant where you have all these columns, and then you can transform through this operation here. So that means that you have, if you look at what you have here and the expression up here, this is nothing but us stating that we take one of these columns from the original one, which is this one, and then just transform one of the columns. So you could think of these A's and B's here. Every column represents a vector, which is orthogonal to all the other ones. Then I transform one of them by a relation like this. And that means that there are some coefficients multiplied with the original basis states. Okay, does that make sense? So this is a relation which applies to the Slater determinant. And that means that if I do this on all the single particle states, so I start with, say, a harmonic oscillator basis here, and I make a transformation to a new basis for all the single particle states in my Slater determinant. Then you can actually rewrite this as a determinant C times a determinant B. This is very important for us because we can use this to show that if the basis we have chosen, the original one, which defines this determinant B, is orthogonal, then the basis of Slater determinants is also going to be orthogonal. So you can actually, with this one, you can rewrite the new Slater determinant in the new basis in terms of all these linear combinations, where these elements, the C's, are actually elements of a unitary transformation of a matrix which represents a unitary transformation. So these are technicalities which I wanted to remind you of because they are relevant for what is going to come now. And the thing I wanted to mention to you, if you now think of the energy, which we have calculated with a reference state, this phi 0, or phi as I call it here, this is given in terms of these matrix elements or integrals. Now, when you calculate with a new Slater determinant, the only thing which changes from this expression to that one is that you have a new basis. However, the new basis, the Romans related to the Greeks, they are now related via transformation like this. So my original basis is this with Greek labels and the new one is Roman letters. That means that when I transform the Slater determinant, this new one, and that's defined by the new basis, which we have up here, then this expectation value, this should actually be phi nu here, actually, not psi. So this is a typo from my side. This one should replace that. You can then actually rewrite everything in terms of the old basis, and then you have these coefficients, which you see here. So we are going to use that when we are going to set up the Hartree-Fock equations. And in the Hartree-Fock equations, we are going to vary these coefficients, like we did for the FCI derivation. But now we're going to vary these coefficients. And when we vary these coefficients and use the variational principle, we are going to get equations for the single particle wave functions, which are modified due to the effect from the many-body medium. So just look at these technicalities, because this is something which we are using again and again. So you have a basis which can be handy, because sometimes if I have a harmonic oscillator basis, this integral here can even be evaluated analytically. So having a handy basis, which is also meaningful physically, means that sometimes, if we are lucky, these integrals have simple expressions or they are easy to evaluate numerically. And that becomes important when we now move to a new basis, which is given by an orthogonal unitary transformation using that old basis. And the thing which is nice is, as well, is that the Slater determinants which we get from that orthogonal basis will also form a basis which is orthogonal. And this is something you will play around with in the exercises. And then this expression which you see here is something which we will now use to derive the Hartree-Fock equations. So the Hartree-Fock equations are derived in two ways often. One is by varying the coefficients, which is going to give us a computational efficient algorithm. Alternatively, you can vary these equations. That is, however, going to lead to what's called an integral differential equation, because we will have a differential in the kinetic energy, and you have to evaluate that integral, which is often computationally expensive because you will need many integration points. And then you also need to evaluate these integrals, which can be time consuming. By just varying the coefficients, as you will see, you will get a set of couple equations which can be solved by eigenvalue problems. And that is much more efficient. So two ways of solving these equations, or two standard ways. One which is historically one, before people started to use eigenvalue problems, because eigenvalue problems actually took off in the 50s and 60s of the previous century. So I don't know how familiar you are with solving differential equations numerically, but one of the approaches which was used very much was something which was called shooting and matching, where you solve the differential equations by setting up a grid, and then you would typically estimate a guess for the energy, and then you would match the wave function by integrating from 0 to infinity and from infinity to 0. And then you would match them at some point, and at the same time tune the energy till the matching point to the wave function from 0 to infinity and from infinity to 0 would match each other. That is a very cumbersome algorithm. And when people started to use linear algebra methods, they could actually solve these differential equation type problems much more efficiently. So we are going to discuss next week also the historical method, which deals with varying these or varying these coefficients here. So I'm just mentioning this because it's a technicality I wanted to bring up. And it's also useful for the exercises this week. Now, the thing which I wanted to do now is actually to bring up something which we have left out, which is a diagrammatic representation of these kind of expectation values, but now with a particle Hall formalism. So any questions so far? So I'm going to switch to the whiteboard now. And we are going to look at all these different Feynman-Goldstone diagrams. So diagrammatic expansions. Or diagrammatic representation. Now, the kind of formalism which I'm following is something you can look up in this textbook by Shavit and Bartlett. And this is something which is described in chapters 3 and 4. And I will follow to a pretty large extent what is in that textbook. So if you wish to read more and see more examples, you will have it there. Now, one of the things which we did in the previous case when we looked at diagrams was simply to stay with a particle formalism. And then we hadn't defined a new vacuum. With a new vacuum, the rules are going to change a little bit. So with new vacuum, we have a contraction which previously was 0. But now this contraction is non-zero. We have the following types of contractions. So we would have an 1, which is an A with an AB. And we know that, no, not that one, the opposite actually. So an AA and an AB. And let me just quickly remind you of that. So that's given now by a contraction on a vacuum state, and B and A are not contained in this new vacuum state. And this is given by delta AB. And we have assumed that A and B are not contained in the vacuum state. So F is still the symbol for the Fermi level. And then we have the new one, where we have this subscripts I and J, which then represents Hall states. So now I have this contraction, which is a delta IJ. And I and J are states which are included in the Fermi vacuum. And the phi 0 contains I and j. If I and j are not contained, then this is obviously 0. Okay, so this is something which we will now make drawings for. So the contraction AB is something we will draw like this. We put a label A, and in principle, we have a line here, a line B, a line A, and these get contracted like this. And similarly, we have now for IA and IJ, but now we are going to look at or write this in a different way. So this is I, and what we will have now actually states which are contracted, and this will be a J and an I. And what is common now? Because in the previous case, when we didn't set up the reference vacuum, the new reference vacuum, was that we didn't put arrows on the lines before after we had done the contractions. But now it's common to mark that these are particle states. So we put arrows before we've taken the contractions. So the previous way we defined these diagrams was an intermediate step, because normally what you end up doing is to run calculations in many-body physics with respect to a given vacuum. So that means that we will normally put lines here like this. So let's take a look now at a specific state, which we would use to calculate, let's say, an expectation value. And one of the things which I wanted to look at now is the expectation value, or this is actually the transition probability, between a state with phi of A, and then I take the Hamiltonian. This is something which we have calculated earlier, but I wanted to repeat that with a diagrammatic representation, because that's going to introduce additional rules when we now are setting up the diagrams, because the rules which we are going to have, they're going to tell us how we can, using a diagram, how we from the diagram can extract the analytical expression for that specific contribution. So diagrams, when we have put labels on them and arrows, they can be immediately translated into an analytical expression. And that expression, to get that one, we need to have some driving rules. And these are the rules which we're going to set up now. So whole lines, in our case now, are downgoing arrows, and particle lines are upgoing arrows. So whole lines are downgoing arrows. And particle lines are obviously upgoing arrows. This is the way we will mark this. So if we now look at one of the states, if I look at the state phi of JB, the way I will mark this one, so this is given by AB, AJ, acting on the reference state, and J is included in the reference state, and B is not. So we are going to mark that one diagrammatically, and here is where I follow the text by Shavit and Bartlett. So we have now a new reference. In our previous example, we had the true vacuum. But now, since we want to distinguish between particles and holes, we are going to label this state as follows. So there will be a particle state B, and there's a hole state J. So this is this specific diagrammatic representation for that state. So I like to mark this with the kind of line here and this shaded area, just to indicate that this is my reference state, my vacuum state. And that means that when I look at the state on the bra side, what I would have then is the following. So if I take the phi I A, that is nothing but an AI AA, and acting on the vacuum state, phi 0. No, sorry. And the drawing we would make then, since this is our end state, so we are back into the reference state, but we have a particle hole excitation. So we would have an A here, and then we have the I here. And then we're going to calculate the expectation value of the Hamiltonian. So let's repeat some of these calculations because it's useful to actually see things again. So we are going now to calculate this quantity here. So there's going to be a one-body operator and there's going to be a two-body operator. So this is going to contain now phi IA. I have the reference state, the reference energy, which is just a constant, plus this operator f of n, plus v of n. So the first term is trivial, because in that case, what we would have is phi of A, IA, and then we have this E0 reference, and then I have my phi J of B. And when we calculate the overlap here, we know that this one, if we take the last one, this is just phi 0 of AA, or AI, AA, AB, AJ of phi 0. And we know that the only contractions which are possible are this one. So this term here, that gives us simply the delta AB and delta IJ multiplied with the reference energy. So if this is a so-called non-diagonal matrix element, this is going to be 0. If it's a diagonal matrix element, then it's going to give us an E0 rep. So diagrammatically then, the way we would write this term here, so let's look at the diagrammatic representation of this first term. So what we would have then would just be something like this. So we have a particle line A, we have a whole line I, and then we have a particle state B and J here. So we would take these contractions like this. And when you look at it graphically, you see quickly that you cannot connect A with a J or A with I because these are different states. So it's very easy to actually see what kind of contractions you should get from that. So that gives us simply delta AB and delta IJ. Now the next term which we have, so we have a new term, which is phi I A, and then we have this f of n and phi j of b. So let's analyze this term. And what we have then is phi 0, and there is a sum of a PQ, and then I have my AI, AA, AP, AQ, and then AB, AJ, and then I have my phi 0, and finally this contains now a specific matrix element, or just an integral, like this. So let's just look at the creation and annihilation operator, and just start looking at the contractions which we get. So the way I'm going to write this now is simply just to look at these AI, AP, AQ, AB, and AJ here. So if the only possible contractions are now the type of contractions here. So these will be particle states, and then these will be whole states. So that's going to put a constraint on delta IJ, or the Kronecker delta, delta AP, and delta QB. And that will give us a contribution which runs like A of F times and B. And it's pretty common to just skip delta IJ. So what happens now when we are doing this diagrammatically is that we get something like this. So we have the state A, I, and then we have the operator. And now I'm just going to write the operator in terms of this box to indicate that this is this operator F. I have left it unspecified, except that's a one-body operator. It has P and Q, I'm not putting labels on it because I haven't done the contractions, but I'm putting labels on the states here because I need to identify in the diagram here which are particle states and which are whole states. So in this specific case, we are contracting that one with that one, and then this is uncontracted. So when we look at the contractions here, this is something which is going to give us a plus sign. And the matrix element we end up with is just this one. And the way we would write this at the end is something like this. So we have a particle state. So we have a B coming in and then being annihilated when it interacts. And then we create a new state, a new particle in a state A. And then there is a bystanding whole state, which doesn't do anything. And it's common to leave that out, unless you want to indicate explicitly that we are dealing with a one particle, one whole excitation, or a state of a given character with an end particle state, etc., whatever it may be. But it's pretty common in the setup of the final diagrams that you just leave these Kronecker deltas, which do not involve the interactions, you just leave them out. So the thing you would list then would just be this quantity here. So that is one of the diagrams we end up with. So the final one which you would list would simply be this term here. So this is the operator. And then I have a particle state coming in and a particle state leaving. So that's that explicit term. So we're a little bit over the hour. So maybe we take a small break, if that's okay. We grab some coffee and just get back in some 15 minutes, if that is okay with everybody. We'll just take a small break. We started a little bit late, so I thought we could just go over time a little bit. So we're going to continue a little bit with these diagrammatic exercises, and then we're going to set up the different rules, which we then can apply when we want to recover the analytical expression from, let's say, something which looks like this. So the expressions which we want to recover are then going to be given by some specific guidelines here. So let's continue a little bit, because now we looked at one specific contraction here, and now we go to the next one. So we have a same set of operators. And in the previous case, we contracted the external particle lines. So we have an AB and an AJ here. Now we are going to take the operators and let them contract with the whole operators, which we have here. So that's one possible contraction which we can have. And then another one which is non-zero is this one. Now, if you now count the interchanges of operators you need in order to get this normal order, you will see that there will be an odd number of contractions. So this is going to give rise to a minus sign. And then we have the final one, which is this one here. So that gives us a minus sign, and I have a delta I. So this is delta IQ, and then I have a delta P with J, and then a delta AB. It's going to give us a matrix element, which is now given by minus, and then I'm going to have a J of F of I, and then I skip this Kronecker delta. It's pretty common just to skip that one. If we look at the diagram, which we are going to get now, when we start with the initial states, which we have, before we make any contractions. So we have this A and I, and then we have the operator here. And we put labels on it, Q, but without putting arrows, because we haven't done the contractions yet, but we put arrows on the particle and whole lines defining the state so that we can distinguish them. So it's a kind of mixed notation compared to what we did before, where we didn't put any arrows when we had only particle states. So we have B and J. And in this specific case, we contract these ones. So that gives rise to delta AB. But now we perform a contraction with J, with P and I with Q. Now, the way you would draw this now, and this can be a little bit confusing in the beginning. So if you look at the matrix element, here you have a J state, which is on the bra side, and you have the I state on the ket side. If you now look at the diagram which you have, so this would lead to the following diagram. And then we draw the whole lines like this. So this would be an I, and this is a J. So what you're saying now, if you look at this, if you tilt it and think of these as particle states. So I'm going to just show you this kind of notation here, which can give you some kind of intuition in the beginning. If you just flip this diagram, what you have now, and you think of these as particle states, this is essentially what it would be. You have a J here and an I here. And that would represent the same kind of process you would have in case you were just looking at the true vacuum, because then everything here would just be particle states, which you create above the true vacuum. So you can think of these one as an incoming whole state I and an outgoing whole state J, which means the same as you are destroying a particle in I and creating one in J. So this is the way you would draw that specific diagram here. Now, when you have this diagram, and you normally, it's common to actually skip the other one, which is this term here, which is normally called a bystanding particle line or bystanding whole line, which does not, which is not involved with the interaction. So we normally call this a passive bystanding fermion, and it's common to just leave that one out. So that means that the kind of diagram you would draw from this type of contractions would just be this one. So that would be a contribution to the energy here, or this specific transition matrix element which we are looking at. So the next thing which we would need to look at now, if we go back to the original expressions, now we took f of n, but we have also the term with v of n. The first term here just gives us two Kronecker deltas, and if I and j are different and a and b are different, that means that this reference energy term will not be present in this specific expectation value or transition probability we are looking at. So let's take the final one and go through both the contractions which you would get by doing the paper and pencil exercises without diagram. And then let's look at how we can represent this diagrammatically. And then based on the diagrams, what we would need then are specific driving rules. So if you look at this contribution which we got here, the analytical expression has a minus sign. So one thing you would do now when you set up the analytical expression to calculate from the diagram is that you would have an outgoing whole line here, which comes in here, an incoming whole line here, which comes in there. And then, since we have now a whole line which goes through the whole diagram, through the contraction here, you get a minus sign. So these whole line contractions give rise to a minus sign when they are being contracted with a specific operator. When they are not contracted with a specific operator, it just gives a plain Kronecker delta with not a minus sign. But the contractions between the whole lines, together with the annihilation and creation operators of a specific operator, they give rise to this minus sign. So that's a kind of driving rule which we are going to set up afterwards. But now I'm just motivating it. When you look at the analytical expression, you have to reproduce by just looking at the diagram. So the final term which we have in this case is the one which involves the two-body interaction. So we have this phi I A, and then we have this V of n, and then we have phi j of b. And the matrix elements, or the contractions which we need to set up in order to find the final matrix element here, is something which involves now AI and then I have AA, and then I'm just taking the two-body operator in terms of the creation and annihilation operators. And then I have AS, AR, and then I have my A, B dagger, and AJ. Now, we looked at this earlier. We actually calculated these expressions, but I just wanted to repeat some of the calculations here. And then we are going to illustrate this with diagrams. Now, what we found, since this operator, which we have here, has a factor 1 divided by 4, we found when we did these contractions, 4 different contractions. But since the matrix elements are anti-symmetrized, we could sum all these 4 contractions. And then there is a factor of 1 divided by 4 here. And these 4 terms are all equal. And then we ended up with just 1 term, 4 divided by 4, and 1 term which was given by the direct term and the exchange term or the anti-symmetrized matrix element. But let me repeat this so that we see it again. It's always useful to see these things several times so that we get a little bit more comfortable with the way we compute these expectation values or transition probabilities and the way we can draw them diagrammatically. So let's go through in a pretty slavish and perhaps boring way these different contractions. So one possibility is that we take these 2 guys and couple them. So this would then be R, would then become a particle state above the Fermi level. And then I could similarly take this one. So that would give me 2 Kronecker deltas. And now the next case I could look at are actually the whole states. Now I cannot take Q with S, that would not be possible because these are operators within the same normal order operator. So I would actually have to take Q with J. So Q becomes a whole state then, and this is an allowed contraction. But then in order to bring everything together, and since you get this kind of crossing contractions line, if you count the number of times you need to interchange the operators to get this as a normal ordered set of all contractions, then I will get a minus sign from this one. So this is going to give me minus delta I S, and then I have a delta Q J, and then I'm going to have a delta AP, and I'm going to have a delta which connects R with B. When I translate this into a specific matrix element, and I take this guy here, because this one contains a matrix element or an integral, so I sometimes I mix interchangeably the integrals and with matrix elements. When I look at this specific contribution, what I get now, there's a minus sign, and then I have my A is given by P, so I have A here, and then I have my Q, which becomes J, and then I have the operator with the 2-body operator, and then I end up with my R being equal to B, and I have this term here, like that. So this is the specific expression which I get, and now I can, since these are anti-symmetrized matrix elements, I can then obviously rewrite this one. If I don't want to have the minus sign, I can have a plus sign, but then I would have AJ, V, and IB here, because these are anti-symmetrized matrix elements. Do you want me to show this again, or is that okay? Because we have this symmetry of the anti-symmetrized matrix elements. So when I interchange 2 labels, we know that that gives a minus sign here. So you can always manipulate them and write them in a specific order. Now, when we now look at this specific contraction here, let's look at it diagrammatically. And then we draw the same states again. So we have the vacuum state here, phi 0. We have an incoming particle line, and we have a whole line. And then we have the operator here with labels P and Q. And then we have an R and S here. And then we have the incoming state, B, and then we have our J here. So if we now look at the contractions which we did, so we had one contraction with the Q and J. So if we go back to that one, so we have Q here being contracted with J. And then we had S, which was then contracted with I. So we get S here with that one. And then we had A with P and R with B. So when we draw this as a diagram, what we will have then is something which looks like this. So I have A here, and I have B here, and then I have a J on this side. So I'm just writing down the matrix element which we put up. So I'm just going to set up this one which came out directly. So what I have then is something which is written as, this is what I want. I have an A, B, no, sorry, A. I'm just reciting the alphabet here. Right? B, and then I had, in this specific case, I have a B and I. This was anti-symmetrized. And then I have one here. And this is something which I would write like this, I and J. Now, when I change them, so I have to be a little bit careful now, because this guy here, this specific one, which we have, this is actually an anti-symmetrized matrix element. So it contains two contributions. So I should actually have used the notation for an anti-symmetrized matrix element, which we defined as so-called Hugenholz diagrams. And that looks like this, I coming in here, we have a J, and then we have the B here, B and A, like that. So the difference when we have particles, lines, and whole lines is now that an outgoing particle state is drawn as this whole line, which looks like something which leaves or comes out of the interaction after it has interacted here. So this is the notation which we would have, because this contribution here, this specific one is now a sum of the direct term here plus an exchange term. So if we are going to write it out, this should also contain something which looks like this. So I have an A and an I here, so we keep these, but then I'm just going to interchange the lines. So there will be a J here, so that would be a whole line, and this would be a particle line, so the B and J down here. But normally this is written in a compact way, since we are using anti-symmetrized matrix elements in this way here. This specific contraction carries a factor 1 divided by 4. Now, there are many ways of writing these diagrams. And one thing you could do now, if you look at this diagram, and this is also a little bit confusing when you look into the literature, is that sometimes people, instead of drawing these diagrams for this one, what they would do is simply to draw this one and at the same time say that this represents this expression. And that can be confusing, and you often have to guess from the context whether they're using anti-symmetrized matrix elements or not. The textbook by Shavit and Bartlett mixes these things, and what they often mean by when they write this is actually this anti-symmetrized matrix element. So this is unfortunately something which can be confusing. So I will try to be explicit now by simply saying that I'm going to use this diagram to indicate this specific matrix element. Now, you will see this represented in another way. So if you take that specific matrix element, which we have with a minus, and then I have an A, J, and V, and BI. If you look at this contribution, AJ of VIB, and if you draw that diagrammatically, what you would have now would be something like this, an A here. There is a J or state I, actually, which now comes in here. So this state I, which you see here, is coming in, or it should be drawn here. What is common then is actually to draw this in a specific way. So what you would do then, when you look at this whole state, you can draw it like this. So there are lots of notations which you will encounter, and you would have a particle state B here. Oh, sorry, not that one. So you have your particle state B here, but then you will draw the whole state J like this. So that's a pretty common way to represent a diagram like that, because then you have a particle hole excitation here. And you have so you can think of you deleting a particle hole pair, and then you create a new particle hole pair. So this is normally called, in physics terms, a one particle, one hole diagram. Because if you look at what you have mathematically, the analytical expression here, you have a particle hole pair here. There is some interaction, and you end up with a new particle hole pair here. At the beginning, it's a little bit confusing because you have this J state as a state which is in the brass side, which is an outgoing state, and you draw the outgoing hole state here. And you have the incoming hole state here. But the way you can think of this, I have a particle hole state, and I end in a particle hole state. So you start then thinking of these as physical processes where you have a one particle, one hole state, which we actually have here. There is an interaction, and that leaves us with a one particle, one hole state. And that's expressed then with the one particle, one hole state here. And then you have your one particle, one hole state here. So if you go back to this image, you see that you start with a BJ and you end with AI, and there is an interaction. So the interaction changes the possible single particle states involved in that particle hole state. So physically, you could now think of you, if you have a diagram here of the different single particle states. Suppose you have these specific states here, and you have a hole here. This is your original state, and you have a particle state here. So this could be your combination BJ. And then you interact, and then you end up with a new one particle, one hole state, where you then have this first one, which is occupied, and then the one which was vacant, which was occupied, is now vacant. And you create a new, so you have a particle hole state here, and you end up with a new particle hole state here. So that's the way you could think of this as a physical mechanism. So these states are different. So the ones which are open, these are slots now which are empty. So this was empty, and now this was filled, but now this is empty. So that would be represented by new particle hole state. And this kind of diagrammatic notation, which you see here, is pretty common for that kind of process. And the only thing we did here was actually to interchange the particle and the hole states, and that gives us, moves us from a minus sign to a plus sign here. But diagrammatically, if you look at this diagram here now, that has a whole line which goes through the whole diagram. And that gives rise to a minus factor. On the other hand, when I look at this diagram here, I don't have a whole line which goes through the whole diagram. I have two whole lines, and two whole lines are actually going, every even number of whole lines is going to give us a factor of plus. So this would be, if we count number of whole lines, we have a hole here and a hole here, but we also have a whole line which goes through the whole diagram. And that gives rise to a factor of minus. So there are going to be some kind of driving rules here, which we are going to set up at the end. Now, when we perform these contractions now, and this is something which we did previously, we are going to get 3 more contributions. And at the end, we can write all of them in terms of just this diagram, times 4, and then divided by 4, as we showed in the previous week. So I won't do all these exercises again, but what we will end up with now is the following expression. And I am setting up this in a diagrammatic way. So it's going to give us a delta Ij and delta AB multiplied with the reference energy, which we would typically just state like this diagrammatically, I and A. And if we assume that they are different, then clearly the reference energy doesn't contribute. And then I get a new term, which now looks like this. And I skip these Kronecker deltas. So I would have an A and B, A here and B, plus, and we always write pluses when we set up diagrams, because the minus sign will come from us using the diagram rules and setting up the final analytical expression. So this would be a whole line, A, I, and J, plus this term which we have here, which we wrote like what you see here. So this can be written that way. No. This is A and I, and then I have my state B and my state J here. If I interchange these whole lines, I would get the other diagram, this one. And it doesn't matter which way you calculate it or which way you present it. But if I use this one, when I'm decoding this and getting the analytical expression, then I will get a minus sign from this piece here, which you wouldn't get from this diagram here. And that diagram, when I translate everything into analytical expressions, so this would simply be E0 ref times delta Ij, delta AB, plus, and then I have my A of F of B times a delta Ij, and then I get a minus, and then I have a J of F of I of delta AB, and plus the final term, an integral, which looks like A of J, V of I, and B. So that will be the final analytical expression, which I will just extract from these diagrams. And if I and J are different and A and B are different, the only term which survives now is actually the last one, this term here. So the diagrammatic way of representing things is an extremely compact way, but we need to set up specific driving rules for doing this. I wanted to show you another case here, and that is the so-called reference energy, which we calculated earlier. And that reference energy contains now the sum of all these integrals of I, H of I, which we normally would just write out as an epsilon of I, if the i's are eigenstates of H0, plus this term which we have here, Ij, and then I have my anti-symmetrized matrix elements, but now I'm going to write them out explicitly. So Vij minus, and then I have Ij of Vji. Now, when we have this double sum here, this makes things a little bit more difficult. But let's try to set up this in terms of the diagram rules for whole states now, because I and J's are wholes. So the first term is going to look something like this. So if we draw it in terms of diagrams, we would have a sum over I less than F. And I would have a whole state I and a whole state I here. And I have this one body operator. Secondly, I would get now minus a plus a half. And then I have my ij. And if I'm now setting these up as diagrams, I would have now the following. So I have my I here and my j here, plus, and I will keep that one. But then I get a cross term here. This will be I and j. Alternatively, I can use these Hugenhaus diagrams. Now, what you have here becomes a little bit, how to say, clumsy, because you have to keep this summation of i's and j's. So what I'm going to do now, instead of keeping these summations, I'm going to do something which is called to close the loops or close the fermion lines. So what I'm going to do now is just to bring these two together, and I'm going to bring these two together, and these two together, and these two together, and the same with that one. And then I'm going to skip the summation signs, and then I'm going to introduce the concept of loops. So these diagrams are now going to be equal to the following. So I'm going to have the interaction, but now I have this loop here where I put a label I, and this represents a whole loop. And it stands now for this summation over all the states below the Fermi level. So this circle here is now, or loop, is now going to represent the summation over all the single particle states below the Fermi level. Then the next term is going to look like this. So I have an I and j, that's this specific term. And then I have finally this term here, which I'm going to write like this, I and j. So this is a very compact expression for these diagrams which I have. And this kind of tadpoles which you see here, they are going simply now to represent the different summations over the Fermi level here. So this is just a very compact summation, very compact representation. So what we are going to get now are additional rules due to the fact that we have holes. So we need now to count the number of hole lines. And that is going to be labeled by NL. And then we need to count the number of closed loops. And in case we have particle lines and hole lines in the diagram, then we actually need to have an additional rules which applies to a diagram like the one which we saw here, and that's going to be given by the number of hole lines which go through the whole diagram. And in this specific case, we don't have hole lines which go through the whole diagram, but if we rewrite it like this, we have a whole line here which goes through the whole diagram through the same vertex. So we also need then to set up the number of hole lines which go through the whole diagram. The whole diagram. So each such term, so if we look at these diagrams which we have here, so let's take a look at the first one and just give labels. This is A, this is B, and this is C. So what we have then is for A, we have this specific diagram, with an I here. So we have a number of holes is equal to 1, and number of loops is equal to 1. There is no through-going line here. We just count the number of holes. This is only, the through-going lines applies only if we don't have closed loops. So in this specific case, that gives rise to a factor which is -1 to nh plus nl, which is equal to +1 in our case. And then when we want to decode the specific contribution here, we're going to get a plus. And then we have the whole line coming in here. We have h0 and I. And that's the analytical expression for that specific term. If x, in this case, is put to h0. So that would be that specific expression. If we go to the next one, which is this one, we put labels I and j. So we see that we have n holes is equal to 2 here, and n loops is equal to 2. So that gives also rise to a factor of +half. Now, there's another factor which comes in if you look at this factor of a half, which we have here. And there is a rule which we need to add, an additional rule. There's going to be a factor of a half because we are summing freely over all single particle states. You could have written this expression, which you see here, with I less than j, and then you would not have had the factor of a half. But if we sum freely, we get an additional rule. So the factor of a half for every pair of fermions or pair of lines, and they have to be either particles or holes, they have to be the same, which start at the same vertex and end at the same vertex. In our case here, we actually have a contribution where you have a whole line which starts at this vertex and ends at that vertex. That's the way you read it. But normally you would have, when you do many-body perturbation theory, you would actually have more interaction terms. And then we will see explicitly then that there has to be a factor of a half when you have pairs of equivalent lines which start at the same vertex and end at the same vertex. So here we would have, when we look at this diagram here, we would actually now get a factor of a half. And then since we are summing, so each closed loop represents a sum, is a sum over these specific states. So what we get then when we write down the analytical expression is, for the first term, we have a plus here. So this gets a plus, and then I have ij here. If we then look at the final one, the C, and then we have a diagram which we wrote like this. So this is I and j. We have fermion pairs, which or equivalent pairs, which end and start at the same vertex. So that gives rise to a factor of a half. But we have only one loop in this case. So this is considered just one loop. So the number of loops is 1. The number of holes is equal to 2 here. And that leads to the expression, which is now minus a half. And then I have to sum over all the single particle states because I have closed a loop, which represents a summation. And then I would have an ij, and then I have the matrix element ij of v and ji here. When I read off the different matrix elements, because I have now interchanged j and I in one of the vertices. So I can then recover from a diagram the specific expressions here. So let's do one last example. If we now take this contribution here, which we discussed some time ago, actually last week, of V of n with a two-particle state, two-particle two-hole state, AB, this is something which we found to be equal to Ij, V, and AB. So diagrammatically, we would actually write this out in the following way. So we have two particle states coming in like this. If you use the rules that A and B, A is to the left as an incoming state and B is to the right as an incoming state for a two-body state. And then we have the particle states I and J. So we would actually write this one like this. And this is something which we would call a two-particle two-hole excitation. So you have a transition here from the ground state, phi 0, the ansatz for the ground state, to a two-particle two-hole state. And we would typically rewrite this in terms of a diagram which represents a two-particle two-hole excitation, where now we have the specific physical process which brings us from the reference state to a two-particle two-hole excitation. So that specific contribution here for that physical process, where we start with a two-particle two-hole state and go back to the vacuum, would then be represented by this diagram here. And we typically call this just a two-particle two-hole excitation or a two-particle two-hole de-excitation, depending on whether we start here and end here. Because diagrammatically, what you would do then is then to have the vacuum state like this. There is nothing here. And then you have your interaction. And then you have the two-particle two-hole state. So with A, B, and then you have the two-hole states. So A and B would contract with these, and these guys would contract with these. So you can think of this as you being in a two-particle two-hole state, and then you de-excite yourself and you get back to the ground state. So normally you would call this a two-particle two-hole de-excitation. If you change it, if you write the other one, what you would get then is phi ij. So you end in a two-particle two-hole state of V of n, and then you have phi 0. Then what you would get would be an AB and V and Ij. And you would draw this in the following way. AI, and then I have my B leaving and J coming in. So this would also be a two-particle two-hole state, but you would call that a two-particle two-hole excitation. So you have created a new state through the interaction, and you would be temporarily in that one, depending on the type of interactions you have and how long this state lives, before you then would return back to the ground state. So this is a kind of interpretation. So you would call this an excitation, and the other one is a de-excitation. Or just loosely, you would just call this a two-particle two-hole excitation, and that's it. So you get a very, how to say, a very nice physical way of interpreting these different diagrams. And that's why it has been so popular, because it gives you a way to talk about physics in terms of this particle hole excitation. As we had in the previous case, we would call the one you see here, this specific diagram, which we wrote down here, we call this a particle hole to a particle hole excitation. So you start in a particle hole state and you end in a particle hole state. So it takes some time to digest all this kind of jargon, but I hope you can see the simplicity which it brings in, that looking at a diagram, you can simply say that this represents a specific physical process. And in particle physics, this was actually what really made this type of processes so popular, or this representation, because you could just look at a diagram and say, okay, this is an electron-electron scattering diagram, or this is an electron annihilation diagram, etc., etc. And every such diagram becomes then a kind of canonical object, in the sense that people refer to that one loosely as this is the physical process. But normally you use this in a kind of perturbation theory or copper cluster theory way of doing it. And then these are just approximations to the full physical process. You've seen this before, right? Yeah. So the only difference between QFT and this is that now we have replaced antiparticles with Hall states. So if you're taking QFT, there's a lot of similarity. Okay, guys, everybody's ready for the weekend, or somebody's even waiting eagerly for the exercises. Okay, happy weekend to everybody.